our last section having to do with derivatives. We are talking about optimization. Now we have kind of touched on this before when we did like those vertical motion problems. And we said, okay, I'm gonna throw a ball up in the air, its movement is modeled by this equation. I gave you some equation. And then I would say, find the maximum height. And what did we have to do to find the maximum height? We had to find our critical points, right? We know from our graphs, critical points are where we have maximums and minimums. So critical points, remember, where the derivative is 0 or undefined. And then we would be able to answer our question from there. So find our critical points and plug it back in depending on how I ask the question. So this section is just dealing with more optimization, which just means maximums and minimums. And anytime I'm asking you for a maximum or a minimum, I'm just asking, where is your derivative, 0 or undefined? So the only difference is I'm not just giving you an equation here, we're going to have to kind of come up with an equation to model each situation. So let's take a look at our process here. So these are just going to be word problems. So we need to, every time, be able to figure out what I'm asking you to find. What is my variable in this instance? You can't solve a problem if you don't know what you're finding. Second thing, we don't want a problem with x, y, and z in it. Okay, so we need to put everything in terms of one variable. If there's multiple unknowns, how can I relate them? Third thing, that's when we use calculus to find the critical points. So we're doing our derivative. Then we can find our maximums and mins from there and answer the question. Word problems, if I give you a problem in words, I'd like for you to answer it in words, so we need to write a sentence at the end to make sure we are answering the question that was asked. I think I tried to put like a blank slide, every other slide here, to give you guys a little more space as we work through these problems. So here is the first one. A farmer has 200 yards of fence to construct 3 sides of a rectangular pen. An existing long straight wall will form the 4th side. So I have a wall, I'm forming a pen on that. What dimensions will maximize the area? All right, at this point, we need to come up with some variables. I don't want to just call these sides x and y because that gives me 2 variables. But we could use that to start with. I'm putting fence on these 3 sides. But what do I know? That's like our perimeter, right? So if I add these up, x plus y plus x, it has to equal 200. So that means my missing side has to be 200 minus 2x. So some people might be able to just look at that and know. Others of us need to work it out. Okay, we just set up an equation. We had 2 variables to start with, but now I figured out what this is. I'm not going to call it y anymore. It's 200 minus 2x. So we did the first step. We figured out what our variable was. It was our width here. We did the second step. Everything is in terms of x. I don't have 2 variables. So now we have to use our calculus. What am I trying to maximize or minimize? Area. So how do we find area? So in the context of my problem, that would be x times 200 minus 2x. Or if I distribute 200x minus 2x squared. Now if I want to maximize or minimize, what do we do? Derivative. You can I'm just going to call this a prime, the derivative of a. So derivative of 200x would be 200, minus derivative of 2x squared would be 4x. And to get our critical points, we set our derivative equal to 0. So we get x to be 50. So the fence should be 50 yards by, how do I find my other side?
15.
Mm-hmm. So I get 200 minus 100 or 100. This is a problem that we would have done last year in pre-calc or college algebra. We just would have said it's a parabola, so finding the vertex of it. So same type of problem, just a different strategy for solving it. Okay. Questions? Is that better than L'Hopital's? So far? Okay, what I want you to do is read the next problem. See if you can draw and label a picture. Okay, you don't have to solve the whole thing yet, just see if you can read it and set up a picture. We need a rectangle. Some of the fencing will be used to construct two inner divider fences, both parallel to the same sides of the crowd. So I didn't tell you which side, you can draw them either way. Our picture isn't necessarily drawn to scale, but we have two inner fences. All right, if I just label these with X's and Y's for a moment, am I putting fence on all the sides this time? Yeah. So I could call these X and these Y. All right. Let's figure out what Y is. We have 1,000 meters of fencing, so what should we do? Good. 4x plus 2y equal to 1,000. Technically, at this point, you can solve for either one. I'll just solve from that y. So if we divide by 2, y is 500 minus 2x. Oh, absolutely. All right. So we set it up, we found our unknown, we put everything in terms of that unknown, so we don't have multiples. Now what do? Derivative of what? I'm trying to find maximum area, so we need an area equation first. Do these inner divider fences change my area? No, it's just length times width. So x times 500 minus 2x. So 500x minus 2x squared. So now we can do our derivative. Derivative of 500x is 500. Derivative of 2x squared would be 4x. And we set that equal to 0. So we divide by 4. And we get 125. Now we just need to go back and make sure we answer the question. So this time I was asked, what is the maximum total area? So I didn't want dimensions this time, I want the area. So what do I do with this? Good. So if I do that, my y, 500 minus 2 times 125. So 250. And length times width, so 125 times 250. And we're in. You could have also just plugged your x back into your area equation. That would have also given it to you. It doesn't matter there. Multiple ways to get to the answer at this point. Any questions on that one? Let's go ahead and do this one. So a piece of metal is rectangular, 5 feet wide and 8 feet long. Congruent squares are to be cut from its 4 corners. So congruent means they're all the same. I'm going to come cut squares out. The resulting metal is to be folded and welded to form an open-topped box. So what happened is we cut this square out, and it's essentially left me with tabs right there. So then if we come in and we fold those 4 tabs up, we get a box. Are you okay with that? We don't know how big these squares were, but we know they're squares, so the sides are the same. So essentially, we could call them x by x. All right, so this length was 5, but I came in and I cut x off this end and x off this end. So now how long is it? Good. This was 8, but I took x off this end and x off this end. So now how long is it? When I folded, these tabs were folded up. How tall is that tab? X. This tab right here, that's the height. So that's x. So that's our box. I am trying to maximize volume. So if I want a maximum volume, I need a formula for volume. How do we find volume? So that's x times 5 minus 2x times 8 minus 2x. Probably easier to go ahead and multiply this out than try to do the product rule with it. Can I FOIL and distribute my x at the same time? If I multiply those, that would be 40 times x, so we get 40x. Minus 10x and minus 16x, so minus 26x times x, so minus 26x squared. Plus 4x squared times x, so plus 4x cubed. If I want the maximum or minimum, what do we do? Derivative. What's that derivative give me?
40 minus 26x.
Minus.
Or sorry, 42, or 52.
Uh-huh.
X plus 12x.
Good. And what do I want to set this equal to? Okay. You can flip it around. But I do think we can reduce. What can all of this be divided by? 4. So we divide by 4 on both sides. Then we can slip and slide. Multiply to 30 and add to negative 13. Negative 10 and negative 3. Divide our 3 back. So that gives me 10/3 and positive 1. Are both of those possible? I mean, there's not anything blatantly wrong, like if I got a negatively, that would be bad. If your metal is 5 feet wide, 10/3, that's like 3.3. If it's 5 feet long, can I cut 3.3 off both ends? No. So 10/3 is too much. If it's 5 feet long, can I cut 1 foot off each end? Yes. 8 feet wide, so I can cut 1 foot off each end. So the question asked me how this should be done. So the squares should be 1 foot wide. So the key to these problems, you have to be able to come up with, sometimes you have to draw a picture or identify your variables, and everything has to be in terms of one variable. We don't want x's and y's. Then you have to look at what I'm trying to maximize or minimize. So that's what I need the equation for. Once you have that, then it's pretty straightforward calculus. We're not having nasty derivatives here. The derivatives are pretty straightforward. Critical points are easy to find. It's the setup that's a little bit harder on these. All right. Questions there? Let's go ahead and just stop there for today. There is a handout posted on Google Classroom. We will continue working on this tomorrow, so it won't be due until Friday at best, depending on how far we get tomorrow. But you could probably do the first, probably even the first 4 problems. There's nothing, it doesn't require anything we haven't seen.